Imagine a spacecraft crossing the bright side of Earth. One half of its hull faces blinding sunlight, the other faces blackness. Both are in the same orbit, only a few feet apart, yet they can be pushed toward brutally different temperatures. And that seems wrong at first. The sun is genuinely hot. It pours energy across the solar system every second. If you stood near a roaring fire, the air around you would warm. So it's reasonable to imagine sunlight doing something similar, turning the space around the sun into one enormous heated room. But space has no room full of air to warm. It's almost empty. Sunlight can cross that emptiness, yet the emptiness doesn't become a warm fluid around you. It doesn't wrap an astronaut in hot air or carry heat onto the dark side of a spacecraft. Light travels through. The vacuum remains a vacuum. That small difference creates some very unfriendly working conditions. In direct sun, a surface can absorb fierce radiation. Move that same surface into shadow, and the incoming sunlight vanishes almost at once. There's no ordinary atmosphere nearby to smooth out the change. Engineers have to prepare spacecraft for both extremes, sometimes on the same vehicle at the same time. So the familiar word temperature starts getting awkward out there. We're used to asking how hot or cold a place is. In space, we also have to ask what is receiving the sunlight, what is hidden from it, and what the nearly empty surroundings can actually do. Tonight, we'll untangle that without treating the answer like a piece of trivia. Why can sunlight feel merciless while nearby shadow becomes dangerous in a completely different way? And what does temperature mean when there is almost nothing there? If you enjoy exploring questions like this with me, subscribing helps others find them too. Liking and sharing the video helps even more. Now, let's begin. When someone says, "Space is cold," it sounds perfectly clear. We say a room is cold. We say the air outside is cold. We say the floor is cold when bare feet meet it in the middle of the night. One phrase seems to cover the whole place. That works fairly well on Earth because our surroundings come bundled together. A room has air, walls, furniture, and light. They trade heat with one another constantly. When you walk into that room, your body joins the exchange. The air touches your skin, the floor touches your feet. Nearby surfaces send out thermal radiation. All those effects arrive together, so calling the room cold is usually good enough. Space doesn't give us that convenient bundle. You can have a blazing source like the sun, almost nothing around it, and an object nearby absorbing its light. Those are connected, but they don't all share one temperature in the familiar sense. There is no thick ocean of air around the sun being heated, stirred, and spread through the solar system. The surrounding vacuum doesn't become a hot fluid bath simply because a hot star is sitting in it. Think of standing near a campfire on a freezing night. Your face warms while the air behind you stays cold. Even here on Earth, the heat source and the surrounding air don't have to agree. Now remove almost all the air. The separation becomes much more severe. An object facing the sun can absorb a strong stream of energy while the emptiness around it remains nearly empty. So the sentence, "space is cold," is usually shorthand. Useful shorthand, certainly, but it leaves out what is supposed to be cold. We might mean the small amount of matter drifting through a region. We might mean the radiation passing through it, or we might mean the temperature reached by a solid surface placed there. Those ideas can be related without giving the same answer. The mistake is treating them as though they belong to one enormous cosmic thermostat. It's an easy mistake because the word temperature came to us through ordinary places. Kitchens, bedrooms, winter streets, places where air, light, and objects are packed close enough to keep affecting one another. We borrow that familiar word, carry it into a vacuum, and expect it to behave exactly as it did at home. It still has physical meaning out there. The problem isn't that temperature becomes nonsense the moment the air disappears. The problem is that the casual question is missing a noun. Temperature of what? That missing noun changes everything. A sparse gas can have particles moving quickly, even while there are too few of them to warm your hand much. A field of radiation can carry its own thermal signature. A surface can settle at a temperature determined by what it absorbs and what it sends away. Calling the entire setting hot or cold folds those different situations into one tidy phrase. And that is the useful correction. The sun can be extremely hot without turning nearby space into the equivalent of a heated room. Its energy crosses the vacuum mainly as radiation. What happens next depends on what receives that energy, how much it absorbs, and how easily it can lose heat again. Before we ask how cold space is, then, we need to be a little more specific. Are we asking about the matter, the radiation, or the surface sitting inside it? Imagine one spacecraft drifting between Earth and Mars. One panel faces the sun, another sits in shadow. The sky behind both looks equally black. It's tempting to assign the whole view a single temperature, as if someone had left a thermometer floating just outside the frame. But which thermometer would we mean? The few particles around the spacecraft can have a temperature. Here, temperature describes how their motion is spread out. A thin gas may contain very little energy overall because there are so few particles, even when those particles are moving quickly, so a high particle temperature doesn't automatically mean the gas would warm your hand very much. There may be almost nothing there to touch it. Light can carry a thermal pattern too. The cosmic microwave background is the clearest example. It fills space with radiation left from the early universe, and its spectrum matches a temperature of about 2.7 Kelvin. That's roughly minus 455 degrees Fahrenheit, or minus 270 degrees Celsius. That number belongs to the radiation field. It isn't a universal setting applied to every rock, satellite, astronaut, and grain of dust. Calling it the temperature of space is convenient, but it quietly changes what the measurement describes. It's a little like reading the color of the light in your kitchen and claiming you've measured the temperature of the table. Then there is the spacecraft itself. Its temperature depends on an energy budget. Sunlight arrives, some is reflected, and some is absorbed. The craft also sends energy away as infrared radiation. Its surfaces settle at temperatures set by how much energy comes in and how much leaves. The sunlit panel receives a strong stream of solar energy. The shadowed panel doesn't. They share the same neighborhood, but they don't share the same temperature. Even one object may be warmer on one side than the other, which is mildly inconvenient if you are hoping space would provide one neat number for the label. Its shape counts too. So does its paint, its angle to the sun, and whether another part of the craft blocks the light. Two identical panels can settle at different temperatures simply because one is tilted. Nothing about their location has changed, their exchange of energy has. These temperatures do interact. Radiation can warm matter. Matter can emit radiation. A spacecraft can collide with the sparse particles around it. Given enough exchange, parts of a system may move toward equilibrium, meaning no net energy keeps flowing between them. But equilibrium isn't guaranteed simply because everything appears in the same patch of sky. Space is too empty, the energy arrives too unevenly, and objects absorb and emit it in different ways. A dark surface and a shiny surface can respond differently. A panel angled toward the sun won't behave like one turned edge-on. The surroundings don't act like the air in a room, nudging everything toward one shared reading. So we need three separate thoughts. Matter has a temperature tied to its particles. Radiation can have a temperature tied to its spectrum. An object reaches a temperature set by its own exchange of energy. These ideas are connected, and they constantly affect one another. They just aren't interchangeable. Once those labels are kept apart, the useful question becomes much simpler. When someone says space is cold, which of those three temperatures are they actually talking about? Put your fingers on an ice cube, and the cold feels immediate. Within seconds, your skin aches. It seems as if the ice is sending cold into your hand. Heat is actually moving the other way. Energy passes from the warmer particles in your fingers into the colder ice. That transfer works because the two materials touch. At the boundary, particles in your skin jostle particles in the thin layer of water and ice beside them. Those particles disturb their neighbors, which disturb the next ones. Energy moves through a material chain. We call that conduction. A glove slows the process. because it places a poor heat-carrying material in the chain. It doesn't stop every transfer, but your hand stays comfortable longer. Pull your hand away and you break direct contact altogether. Your fingers and the ice can no longer exchange energy by conduction across the open gap. Now imagine the glove reaching into empty space. There's no ice waiting for your fingertips, no cold wall, almost no neighboring particles outside the glove to carry energy away through collision after collision. The material bridge is missing. Conduction through the surrounding vacuum has nowhere to go. That doesn't mean conduction has vanished inside your glove, your spacesuit, or a spacecraft. Their materials still touch. Heat can travel along a metal frame, through a window, or between layers joined together. A warm electronic component can conduct heat into the panel holding it. Engineers have to account for all of that. Vacuum only removes the external route that would depend on contact with surrounding matter. The second route is easier to feel on your face. Stand outside on a cold, windy day, and moving air keeps replacing the air your skin has already warmed. Each fresh bit of air takes some energy, moves on, and makes room for more. Water can do this very efficiently too. That's why cool water can drain warmth from your body much faster than still air at the same temperature. That is convection. Heat travels because a fluid moves. The fluid might be air, water, another gas, or another liquid. Whatever it is, something has to flow past the warmer object, take up energy, and carry that energy elsewhere. In a vacuum, there's no surrounding breeze. There's no ocean current slipping over the hull. Air inside a spacecraft can still circulate and move heat around the cabin. Fans may even be needed to keep warm pockets from forming around equipment. Outside, though, the fluid needed for convection is absent. You could wave a gloved hand through the emptiness and create no cooling wind at all. There's almost nothing there to push. So two familiar sensations disappear together. Space can't press against you like an ice cube, and it can't strip warmth away like winter air. The roots behind many cold experiences on Earth depend on matter connecting the warmer thing to cooler surroundings. One needs touching particles, the other needs flowing particles. Remove that connection outside the object, and both routes fail. Yet an object in space can still lose energy. A spacecraft can overheat on one side and become severely cold on another, even though no icy surface touches it and no wind crosses its hull. If contact and moving fluid are both gone, what route is left for the heat to take? You already know this route. Sit near a campfire and hold out your hands. You don't need to touch the flames. You don't even need the warm air to blow toward you. Across the dark gap, your skin begins to warm. Some of that warmth may arrive through moving air, especially if the wind shifts. But the glow itself carries energy. Put a solid screen between your hands and the fire, and the warmth drops almost at once, even though the air around you hasn't had time to change much. Remove the screen, and you feel the fire again. Something crossed the gap, and it wasn't a stream of hot air. That transfer is thermal radiation. Every object with a temperature emits electromagnetic energy. The hotter it is, the more energy it generally sends out, and the balance of wavelengths changes with temperature. A campfire gives off visible light, which your eyes catch, and plenty of infrared, which your skin feels as warmth. The useful part is that electromagnetic waves don't need matter to carry them. They can cross air, pass through some materials, and travel through empty space. No chain of touching atoms has to pass the energy along. No moving gas has to sweep it away. The warmer object emits energy here. Another object absorbs some of it over there. The missing material bridge has been replaced by energy that can travel through a vacuum. You see the result every clear day. The Sun is about 93 million miles from Earth, or roughly 150 million kilometers away. Almost all of that distance is near vacuum. There's no warm breeze blowing from the Sun to your face. There's no solid surface joining the Sun to the ground beneath your feet. Yet sunlight crosses that gap, strikes your skin, a roof, a spacecraft panel, or the ocean, and some of its energy is absorbed. Once absorbed, that energy joins the motion inside the material. Molecules jiggle more, the surface warms. Sunlight has crossed empty space as electromagnetic radiation, and delivered energy without bringing along a hot piece of the sun, which is probably for the best. The exchange also works in the other direction. A warm spacecraft emits radiation outward. If it sends away more energy than it absorbs, it cools. It can radiate toward colder surroundings with no air, water, or metal between them. Empty space hasn't stopped the transfer. It has merely removed the other routes. And everything with a temperature participates, even when it doesn't glow visibly. Your body is radiating now. So are the walls around you. Most of that energy is infrared, beyond what your eyes can see. Visible glow is only the showy part of a much broader exchange. That doesn't mean radiation always cools something quickly. The rate depends on temperature, surface properties, exposed area, and what radiation is arriving from elsewhere. Different wavelengths can also be absorbed, reflected, or transmitted differently. A surface isn't simply open or closed to all radiation at once. But the basic route is wonderfully spare. Warm matter emits electromagnetic energy. That energy crosses the gap. Other matter may absorb it. This is how a star can warm a distant spacecraft, and how that same spacecraft can shed energy into space. So the vacuum isn't thermally silent after all. It carries light, infrared, and other electromagnetic radiation without needing a material messenger. With that route still open, what decides whether an object in space warms up or cools down? You might view sunlight near Earth as something like a hot wind. It pours through the whole region, so surely the region itself must become hot. That would make perfect sense in a room. Warm air reaches you from every direction, touches your skin, and carries energy into anything cooler than itself. Sunlight doesn't work that way. Imagine holding a dark panel directly toward the sun with a meter attached to its back. The meter isn't measuring the temperature of empty space. It's counting how much radiant energy arrives at the panel. At Earth's distance, with the panel facing the sun, the incoming sunlight is about 1,361 watts per square meter. That's roughly 126 watts per square foot. Imagine 12 ordinary 100-watt light bulbs concentrating their full output onto an area about the size of a small dining table. The comparison isn't exact, because bulbs send energy in many directions while sunlight arrives as a beam, but it gives your body some sense of the number. This is no weak trace of energy slipping through the dark. It's a substantial, measurable stream. A spacecraft instrument can follow small changes in that stream. Turn the panel away from the sun, and the reading falls. Place it in shadow, and most direct sunlight disappears. Face it squarely into the beam, and the full input returns. The energy was crossing the vacuum all along. The panel simply gave it somewhere to land, and something solid to affect. And that last part counts. A watt measures a rate of energy transfer. It tells you how quickly energy is arriving, not what temperature the receiving object must have. Temperature belongs to matter with energy distributed among its particles. The sunlight between the sun and the panel is energy in transit, carrying a considerable input without becoming warm air along the way. A sunbeam can still have local effects before it reaches a solid surface. It can push very gently on matter. It can scatter from dust. It can be absorbed by stray atoms or charged particles. Empty space is never perfectly empty. But the thin material out there isn't behaving like warm air in a heated room. It doesn't store the sun's output as a surrounding bath that presses against every surface. Think of water moving through a clear pipe. A flow meter can tell you how many gallons pass each minute, but that number alone doesn't tell you how deep the water will become in a bucket. You still need to know the size of the bucket, whether water leaks out, and how long the flow continues. Solar flux is similar. It tells us the incoming rate. What happens afterward depends on the target. A bright metal sheet may reflect much of the beam. A dark surface may absorb more. A thin object may warm quickly because there isn't much material to heat. A larger object may accept the same input per square meter yet change temperature more slowly. None of those outcomes is contained in the number 1,361 by itself. So yes, the sun sends a powerful beam through the space around Earth. Instruments can measure it cleanly, and exposed objects can't ignore it. But a strong flow of energy through empty space is not the same thing as empty space being hot. The beam is real. The hot environment you imagined is not. Imagine a strip of afternoon sunlight crossing your living room. You can see it pass through the window, over the floor, and onto a dark couch. Put your hand on the cushion, and it may feel surprisingly warm. Hold your hand in the bright gap just above it, and the air feels fairly ordinary. The sunlight crossed both places, but the couch took it in. That simple difference is the missing step between incoming light and temperature. Light can carry energy across a distance without warming the distance itself. Local heating begins when matter absorbs that energy. The fabric, foam, wood, or skin catches some of the incoming radiation. Its atoms and molecules gain energy. The surface warms, and then it has to do something with that heat. It may store some for a while. It may pass some deeper into the object, and it may send some away again as infrared radiation. The clear gap doesn't offer much material to absorb the beam, so most of the light keeps going until it meets a target. In your living room, there is still air, of course. Some wavelengths interact with that air, and warm surfaces can heat it afterward, so the room isn't a perfect model of space. It gives us only the useful part. The beam crosses the gap, while the target does most of the warming. Remove nearly all the air, and that distinction becomes cleaner. The sunlight can travel through empty space for millions of miles without turning the emptiness into a hot bath. Then it reaches a spacesuit, a satellite panel, or the side of a spacecraft. That surface absorbs some fraction of the light, and the heating happens there. Until the light strikes matter, it is energy in transit, not a temperature waiting in the gap. Not every surface accepts the same fraction. A dark material may absorb a great deal. A bright or reflective material may send much of the light away before it becomes heat. Two objects placed in the same solar beam can therefore settle at very different temperatures. One can become painfully hot while the other stays comparatively cool, even though the same sunlight reaches both. The beam alone doesn't dictate the result. The target gets a vote. And that is why spacecraft designers care so much about surfaces. A shiny outer layer isn't merely decorative, and a white spacesuit isn't chosen because white looks tidy against black space. Surface materials help control how much solar energy gets absorbed. Exposure counts too. One side may face the sun while another sits in shadow, leaving a single object with very different conditions across it. For a spacecraft, choosing its outer skin is part of choosing how it handles sunlight. And there is a mildly absurd human version of this. An astronaut can be surrounded by almost nothing, yet still need protection from overheating. The danger isn't hot space pressing against the suit, it is sunlight landing on the suit, being absorbed by real material and becoming heat that must be managed. So the couch warms, while the bright gap above it mostly doesn't. In space, the same rule holds with the room stripped away. Emptiness carries the light. Matter turns that light into a local temperature. But if the surface is where the heating happens, what decides exactly how hot that surface gets? Once sunlight reaches a surface, it's tempting to treat the rest as simple arithmetic. More sunlight means more heat. Less sunlight means less heat. And if two objects receive the same amount, you might expect them to settle at roughly the same temperature. That would work if energy only traveled in one direction. Think of a household budget. Money comes in, money goes out, and the amount in the account depends on both. Knowing the income helps, but it doesn't tell you the balance unless you also know how quickly money is leaving. A surface in sunlight keeps a similar energy ledger. Solar irradiance is the energy arriving from the sun. Some light may be reflected, while some is absorbed. But after the absorbed light becomes heat, the ledger stays open. The surface is losing energy at the same time. Anything warmer than absolute zero gives off radiation. You're doing it now. So is the wall beside you, the glass in the window, and the cold metal frame around it. Much of that energy leaves as infrared light, which your eyes can't see. A thermal camera can. Through one of those cameras, every warm object carries a quiet glow. A spacecraft does the same thing. A sunlit panel absorbs incoming light while sending infrared energy away. One set of arrows points inward from the sun, another set points outward from the panel. Its temperature develops between those two flows. Temperature in space depends on the balance between energy absorbed and energy emitted. If a surface absorbs energy faster than it emits energy, its temperature rises. As it warms, it radiates more strongly. With enough time under steady conditions, the energy leaving may come to match the energy being absorbed. The temperature then stops climbing, even though sunlight is still pouring in. The sunlight hasn't stopped heating the surface. The surface has simply begun losing energy at the same rate. Energy arrives, energy leaves, and its stored heat no longer changes. The reverse is equally ordinary. If a surface sends energy away faster than it absorbs new energy, it cools. As it cools, its infrared glow weakens, so the rate of energy loss falls. Another balance may eventually develop. But real objects don't always settle quickly, neatly, or at one unchanging temperature. A spacecraft can pass into shadow. A rock can rotate between day and night. Thick material can hold heat inside while its outer surface changes. Even a steady beam of sunlight can produce a temperature that keeps shifting for quite a while. That doesn't make the ledger useless. It means the figures are moving. At every moment, energy is arriving and energy is leaving. The difference between those flows changes how much heat the object stores. This is why incoming sunlight is only an input. It isn't a temperature reading. It tells you how much solar energy reaches a location, but not the temperature every object there must have. Two objects at the same distance from the sun can receive similar sunlight and still end up at different temperatures. To know why, you have to follow both sides of the ledger, what each surface absorbs and what each surface sends away. So distance gives you part of the answer. Sunlight gives you part of the answer. Neither settles the temperature alone. Once energy can leave as well as arrive, equal distance no longer guarantees an equal result. Imagine two cars parked side by side at noon. One is glossy white, the other is matte black. They sit under the same sun, in the same air, for the same amount of time. Yet, when you place a hand near each hood, they don't feel remotely alike. The dark hood has kept more of the light that reached it. The white hood has sent more of that light away. A surface does something similar in space. Some incoming light bounces off. The rest is absorbed and becomes heat. Reflectivity describes how large that bounced share is. A bright, icy surface can reject much of the sunlight falling on it. A dark, rocky surface may keep far more. Equal sunlight arrives, but unequal heating begins almost immediately. The angle counts too. Hold a flashlight straight against a wall, and its light gathers into a small, bright patch. Tilt the flashlight, and the same light spreads across a wider area. Sunlight works that way on a curved object. Near the point facing the sun, the energy is concentrated. Toward the edges, it arrives at a slant and spreads thinly. So even one perfectly uniform world wouldn't heat evenly across its surface. Then there's the way heat leaves. A warm surface gives energy back as infrared radiation, a kind of light your eyes can't see. Different materials do this with different effectiveness. That property is called emissivity. A surface that emits infrared energy efficiently can shed heat readily. Another surface may hold on to heat longer, even after absorbing a similar amount of sunlight. This can feel slightly unfair. You've finally balanced the incoming and outgoing energy, only to discover that the surface itself is quietly editing both columns. The equation may be tidy. The object sitting in the sunlight is under no obligation to be. Movement changes the result again. Imagine one dark object always showing the same face to the sun. Its lit side keeps receiving energy while its dark side keeps losing it. The contrast can become severe. Now let that object rotate. Each patch moves through light and darkness, so heating and cooling are shared around the surface. Faster rotation often softens the difference between day and night, though the material beneath the surface still gets a vote. That vote is thermal inertia, how slowly something warms and cools. Dry dust near the top can heat quickly in sunlight and lose that heat quickly after dark. Dense rock can take longer to warm, then release stored heat for hours. It behaves a little like a thick baking stone after the oven is switched off. The air nearby may cool, but the stone keeps giving back the energy it stored. Put those effects together and distance starts to look like a rather blunt clue. Two objects can occupy the same band of sunlight, while one is dark, slow turning and quick to change temperature, and the other is reflective, rotating and able to spread heat through deeper material. Their thermal lives will be different, even before atmospheres, internal heat and other influences join the view. Reflectivity decides how much light stays. Emissivity helps decide how quickly heat escapes. Rotation moves surfaces between day and night. Thermal inertia decides how sharply they respond. The sun supplies the energy, but the object's surface writes much of the answer. It's tempting to give every orbit a temperature, as if a spacecraft crossing that invisible track has entered a room with the thermostat already set. But view one spacecraft in sunlight. Its front face looks straight at the sun. A panel beneath it looks toward the bright Earth. A radiator on the other side looks into dark space. Another surface sits in shadow behind the main body. They're all traveling together. Same speed, same altitude, same orbit. Yet they aren't living in the same thermal surroundings. Calling the orbit hot or cold is a little like describing an entire house by the temperature beside one window. It tells you something, but not enough about any particular room. The sun-facing side receives direct sunlight for as long as that angle lasts. The Earth-facing side may receive sunlight reflected from clouds, oceans and land, along with infrared heat radiated by the planet itself. The radiator may have a wide, clean view of darker sky, which gives its heat somewhere useful to go. A shadowed panel might miss the sun, but still see a warm part of the spacecraft beside it. That phrase, what it sees, is surprisingly close to the whole trick. A surface exchanges radiation with whatever lies in its line of sight. Bright source, warm planet, dark sky, hot engine housing, nearby panel. Change that view, and you change the balance. Even a small shift in orientation can hide one source and reveal another. Nothing about the orbit has changed. The thermal world of that surface has. Time counts too. A brief turn toward the sun may warm only the outer layers. A long exposure lets heat work farther inward. Then the spacecraft enters shadow, and each part cools according to what it can see and how easily stored heat can reach the surface. Two panels that looked nearly identical a few minutes earlier can now drift apart. Their recent histories travel with them. Meanwhile, the spacecraft is making heat of its own. Electronics run, batteries charge and discharge, instruments operate. That energy doesn't politely vanish after doing its job. It becomes heat, and the heat must travel through joints, frames, pipes, panels, and coatings until some surface can radiate it away. So the outward-facing radiator may be cold in one sense and busy in another. It avoids unwanted sunlight, yet receives heat from inside. The sun-facing panel may be taking in plenty of energy while conducting some of it toward cooler structure. The shadowed side may cool quickly or stay warmer because a neighboring component keeps feeding it heat. Even surfaces that share the same metal frame can be pulled in different directions at once. Engineers don't leave all of this to chance. They choose coatings, insulation, radiator positions, conductive paths, heaters, and spacecraft orientation to keep the differences within useful limits. And not every orbit produces the same extremes. Some environments are steadier than others, and well-designed spacecraft control much of the variation. The point is simpler. The orbit's name doesn't settle the temperature. What looked like one object in one place is really several thermal worlds bolted together. One face sees the sun, one sees Earth, one sees the dark. Inside, heat searches for an exit. The trick was visible the whole time. We had simply given the orbit a single temperature when the surfaces were each answering a different set of surroundings. And when those separate thermal worlds have to protect a living human body, how do you keep every one of them under control? Imagine an astronaut working outside the station. One side of the white suit shines almost painfully bright. The other seems to disappear into the black behind it. The astronaut may be only a few inches thick, but those two sides are living in very different surroundings. NASA gives a blunt range for spacewalk exposure, roughly minus 250 degrees Fahrenheit to plus 250 degrees Fahrenheit. That's about minus 157 to plus 121 degrees Celsius, a swing of 500 Fahrenheit degrees, nearly 280 Celsius degrees, all around one person close to home. Those are environmental exposure conditions. They're not the astronaut's core body temperature, and they don't mean a person inside the suit is being heated or chilled to either extreme. The suit is there precisely to prevent that. Still, the range tells you what the suit has to manage while someone works inside it. On Earth, air keeps interfering. Warm air rises, cooler air moves in, wind crosses a surface. Even on a still day, the atmosphere carries heat around and softens some of the difference between light and shade. Vacuum offers no such help. There's no surrounding air to mix the hot side with the cold side. So the surface facing the sun can absorb intense radiation, while the shaded surface loses heat into darkness. They can be close enough to touch and still head in opposite thermal directions. The bright half doesn't share its warmth through a convenient layer of air. The dark half doesn't receive any warmth that way either. This creates a slightly absurd problem. Space is famous for being cold, yet an astronaut can overheat there. Sunlight is famous for being hot, yet an astronaut can still lose dangerous amounts of heat. Neither label tells you what happens to the whole person. Inside the suit, the astronaut is also making heat. Muscles work, electronics run. The body keeps turning food into warmth, even while the outside environment swings between extremes. During hard physical work, getting rid of that heat can become as important as keeping the cold out. A sealed suit cannot simply open a vent and enjoy a breeze. That is why a spacesuit is less like a thick winter coat and more like a tiny spacecraft shaped around a person. Its outer layers reflect and block radiation. Its insulation slows unwanted heat flow. Beneath those layers, cooling equipment carries body heat away and releases it under controlled conditions. The suit has to defend against heat arriving from outside, preserve heat when the surroundings pull it away, and remove the heat produced by the person inside. And it has to do those jobs at the same time. An astronaut can turn, reach, enter shadow, or come back into full sunlight. A hand may be pointed one way while the backpack faces another. The thermal problem changes with posture, sometimes in the middle of a single task. So the range from minus 250 to plus 250 degrees Fahrenheit, minus 157 to plus 121 Celsius, is not a prediction of what happens to the astronaut's flesh. It describes the fierce exposure surrounding a protected human being. The same orbit can threaten overheating and freezing, sometimes across the same suit. What sounded like a puzzle about whether space is hot or cold has become something more practical, keeping one living body comfortable between both. You might expect cold space to do us one small favor. If an astronaut or spacecraft gets too warm, surely all that cold emptiness should soak up the extra heat. But emptiness is exactly the problem. There's no cold breeze outside the suit. No surrounding air flows past it and carries warmth away. Inside, the astronaut's body keeps producing heat. Electronics do too. Every pump, battery, computer, and motor adds a little more. Think of standing in front of a fan after walking up a steep hill. Moving air pulls heat from your skin and carries it across the room. Now switch off the fan, remove the room, and keep exercising inside several protective layers. You're still making heat. You've simply lost one of the easiest ways to remove it. In a vacuum, that heat must eventually leave as radiation. Warm surfaces give off energy as infrared light, which your eyes can't see. The warmer the surface, the more energy it can send away. But that only works well when the warm surface has somewhere useful to send it. And this is where the problem becomes partly about shape and direction. A radiator pointed toward dark space can release heat effectively. Point that same radiator toward the hot side of a nearby spacecraft, the sunlit Earth, or direct sunlight, and it may absorb more energy while trying to cool itself. A surface can't simply know that space in general is cold. It responds to whatever fills its view. That makes a spacecraft radiator, rather like a person looking for a cool place to stand at a crowded barbecue. The night air may be chilly, but standing beside the grill won't help. Where you face counts. What surrounds you counts. Even your angle counts. Spacesuits handle this with several systems working together. Reflective outer layers limit incoming sunlight. Insulating layers slow unwanted heat moving in either direction. Inside the suit, cooling equipment collects heat from the astronaut's body. That heat is carried away through a controlled system, then released where the suit's design allows it. The insulation doesn't solve everything by itself. A perfectly insulated astronaut would keep gaining heat from their own body until the inside became dangerously warm. Insulation slows heat. It doesn't make heat disappear. Spacecraft have the same awkward obligation on a larger scale. Their reflective surfaces, insulation, heaters, pumps, coolant loops, and radiators have to work as one thermal system. Engineers also have to consider the craft's orientation. A radiator may need a clear view of deep space, while other surfaces shield it from sunlight or warm objects nearby. So waste heat rejection isn't just a contest between a hot machine and a cold universe. It's a geometry problem. Heat must travel through the spacecraft, reach the right surface, and leave in a direction that won't send much energy back. On Earth, cooling often happens around us without permission. Air moves, water circulates. Warmth leaks into walls, floors, and weather. In space, almost every useful path for heat has to be provided on purpose. Cold space does not cool you for free. It gives you a dark place to radiate into if you can keep that view open and guide the heat there. Thermal control is designed, aimed, and managed. Without that careful route outward, even the coldest surroundings can hold a very warm problem. Burning and freezing sound like opposite problems. On a spacecraft, they can happen a few feet apart. Imagine one machine moving through sunlight. One side faces the sun and absorbs energy. Another side looks into darkness and loses heat by radiation. Between them sit computers, batteries, instruments, and people, all producing heat of their own. The spacecraft isn't choosing between a hot environment and a cold one. It's dealing with several different thermal conditions at the same time. A kitchen can give you a rough view. Imagine cooking beside an open freezer while someone has left a laptop running on the counter. The stove warms one side of you. The freezer pulls warmth from the other. The laptop adds a smaller, steady source that still has to go somewhere. None of those effects cancels the others neatly. You have to control each path. A spacecraft works under a stricter version of that problem. Every outer surface has its own view. A panel aimed toward the sun may take in more energy than engineers want. A shaded panel may radiate heat away too quickly for the equipment behind it. A radiator needs a clear view of cold space, yet it must also avoid absorbing too much sunlight or heat reflected from a nearby planet. Even surfaces attached to the same frame can need very different treatment. And those surfaces are connected. Heat entering through one area can travel through the structure towards something that was already warm. Meanwhile, a nearby instrument may need protection from losing heat through its own exposed panel. So the problem isn't solved by declaring one side hot and the other cold. The whole machine has to be considered at once. That's why thermal control isn't simply insulation, and it isn't simply cooling. Insulation can slow unwanted heat flow, but slowing heat also makes it harder for internal waste heat to escape. A highly reflective surface can reject sunlight, while a darker or specially coated surface may be useful for releasing heat. Heaters protect parts that would otherwise become too cold. Radiators give warm equipment a deliberate route outward. Sometimes heat pipes carry energy from a crowded interior to a surface better placed to release it. The awkward part is that the machine keeps moving. Sun and shade are neighboring states along one orbit. A spacecraft may pass from sunlight into a planet's shadow, then return to sunlight again. Its surfaces can also point in new directions as antennas, cameras, or solar arrays move. The thermal design has to tolerate those changes without letting one component cook while another slips below its working temperature. There isn't one balance that fits every mission. A probe near the Sun faces a different set of heat loads from a telescope operating far beyond Earth. A spinning spacecraft distributes sunlight differently from one that holds a fixed orientation. The useful radiator placement, coatings, heaters, and internal heat paths depend on where the machine travels and what it must do there. Still, the shared lesson is simple. Hot and cold in orbit aren't rival climates. They're competing flows of energy across one object. Engineers manage which surfaces absorb heat, which surfaces release it, and how warmth travels between them. The spacecraft survives because those paths have been arranged to work together. But a spacecraft can carry insulation, heaters, radiators, and carefully chosen surfaces. What happens when the object crossing from sunlight into shadow is an entire natural world with no atmosphere to soften the change? You might expect the Moon to settle into a reasonable middle temperature. It has been circling under the same sun for billions of years. Surely all that heating and cooling should average out somehow. But a surface doesn't experience an average. It experiences whatever is happening now. And, on the Moon, now can last for an almost ridiculous amount of time. Stand in one lunar spot as the sun rises, and daylight doesn't hurry past. The sun creeps across the sky, morning stretches on, noon takes its time arriving. That patch of ground can remain in sunlight for roughly 15 Earth days. Think about leaving a dark stone on a sunny windowsill. After a few minutes, it feels warm. Leave it there through the afternoon, and it becomes much hotter. The Moon does something similar, except the afternoon lasts longer than 2 full weeks on Earth. There's no evening breeze arriving at 6, no cloud drifting over, no damp soil carrying some of the energy away. The sunlight keeps coming. In some daylit regions, the lunar surface can reach about 127 degrees Celsius. That's roughly 260 degrees Fahrenheit. Hot enough that our ordinary idea of a cold, airless moon becomes rather awkward. The Moon is cold in many places and at many times, but sunlight can make its exposed surface fiercely hot. That temperature isn't reached everywhere the sun touches. The angle of the light counts. So does the slope of the ground, the local time, and the properties of the surface itself. A sunlit crater wall won't necessarily behave like a flat plane near lunar noon. The number describes the hotter conditions found in some regions, not one uniform temperature painted across the bright half of the Moon. Still, the Moon gives us a remarkably clean natural experiment. It removes nearly all the familiar systems that keep Earth's surface from responding so directly. On Earth, air moves heat around. Oceans absorb huge amounts of energy and release it slowly. Clouds can block sunlight before it reaches the ground. Water evaporates, winds shift, and night usually returns within hours. Even soil and vegetation help spread energy through depth, moisture, and living material. We rarely leave a landscape beneath uninterrupted sunshine for anything resembling 15 days. The Moon has almost none of that help. Sunlight arrives as radiation and warms the material it strikes. The ground can conduct some heat downward, but lunar soil is loose and insulating, so that transfer is limited. With no substantial atmosphere and no oceans, there's little machinery for carrying the absorbed energy somewhere else. So the surface keeps taking in sunlight for days, then more days, then another week. The long lunar day gives radiative heating time to build. By lunar noon, the ground has spent an extraordinary stretch facing the sun with very little moderation. Nothing about the sunlight itself has become more aggressive. It's the same sun that warms your pavement, your roof, and the hood of a parked car. What changes is the world receiving it. Strip away the air, the water, the clouds, the weather, and a quick return of night, and sunlight's effect becomes much easier to see. The Moon doesn't average its way into comfort. Its surface follows the energy available in each place over the time that energy is allowed to act. Under 15 Earth days of daylight, some lunar ground climbs to about 127 degrees Celsius, or 260 degrees Fahrenheit. Same sun, far less moderation, and the dust gets very hot indeed. You might expect all that heat to linger. After nearly 15 Earth days in sunlight, the lunar ground has had plenty of time to warm. Here on Earth, a brick wall can stay warm long after sunset. A road can release the day's heat beneath your feet. Even the soil in a garden holds something back. The Moon's surface does hold some heat. It just doesn't hold very much near the top. Lunar soil, called regolith, is loose and powdery, with countless tiny gaps between its grains. Heat doesn't travel through it well, so the warmth gathered at the surface has only a shallow reserve beneath it. There's no deep, dependable bank of stored energy ready to carry the ground through the night. It's more like a warm crust resting on material that won't readily share its heat. And that night is patient. A place near the lunar equator can remain in darkness for about 15 Earth days. For 2 weeks, the same pale ground that sat in white glare faces black sky instead. It keeps sending energy away as infrared radiation, little by little, hour after hour. On Earth, the air helps slow that loss. The ground warms the atmosphere, and gases in the atmosphere send some infrared energy back down. Clouds can add another layer of insulation. Air also moves heat between places, while oceans and damp soil store enormous amounts of it. None of that makes an Earth night perfectly gentle, of course, but it gives the surface company. On the Moon, there's almost no atmosphere to return warmth to the ground. Once sunlight leaves a particular patch, the main incoming supply is gone. The surface continues radiating energy into space, with very little arriving to replace it. The long darkness gives that cooling an uninterrupted run. By the end of the lunar night, some surface temperatures can fall to about -173 degrees Celsius. That's about -280 degrees Fahrenheit. Not merely cold enough for frost, or a deep winter coat or any freezer you've met. -280 Fahrenheit. And the ground reached that temperature under the same sun that had recently helped drive nearby daytime soil above the boiling point of water. This doesn't mean the whole Moon cools together, or that every place reaches the same number. The poles, the equator, crater walls, slopes, shadows, and different kinds of ground each have their own pattern. Nor does the entire lunar interior become that cold. These are surface conditions, shaped by where the sunlight falls and how easily heat moves through the material below. The change also isn't instant. Sunset begins a slow withdrawal. The bright dust dims, the surface loses energy, and the temperature keeps falling through a night measured in Earth weeks. There's no sudden plunge imposed by space, just a long imbalance between what leaves and what comes back. So the Moon's nighttime cold isn't a separate trick from its daytime heat. Both reveal the same missing protection. In daylight, energy arrives and meets little resistance. In darkness, energy departs and receives little replacement. The sun hasn't weakened, the ground hasn't entered some colder region of space. Only the local balance has changed, and on the Moon, balance offers almost no middle ground. Almost no middle ground, but not quite none. Imagine walking across the lunar surface toward a deep opening in the ground. Outside, the sun is pouring energy onto the dust. A few steps farther, the floor drops away into shadow. Down there, some lunar pits remain near 63 degrees Fahrenheit, about 17 degrees Celsius. That's roughly the temperature of a cool room. It sounds almost misplaced on the Moon. And this is an airless world where an ordinary patch of ground can become brutally hot, then bitterly cold. Yet inside certain pits, measurements suggest a much narrower and steadier range. The Moon, it turns out, doesn't have one simple thermal personality. A small change in shape can create a very different local balance. You can feel the basic idea beneath a porch roof on a sunny day. The roof doesn't cool the entire neighborhood. It simply blocks the sun from reaching one particular place. A lunar pit does something similar, though with no air carrying warmth around. Its walls and overhangs limit which surfaces receive direct sunlight. Parts of the cavity spend much more time in shade. Shade explains only half of it. At night, an exposed patch of lunar soil has a clear view of the dark sky. It can radiate its heat away freely. A surface inside a pit sees more rock and less open space. Some of the energy leaving one wall reaches another wall instead of escaping immediately. The cavity shelters its interior from direct heating, while also slowing some of its radiative cooling. The same geometry softens both sides of the swing. That doesn't mean every corner of every pit sits neatly at 63 degrees Fahrenheit or 17 degrees Celsius. Sunlit walls, shadowed floors, depth, angle, and local rock all matter. One ledge might catch light while another stays hidden. The temperature can change over short distances, and a comfortable reading at one location doesn't turn the whole cavity into a ready-made home. Still, the thermal lesson is remarkably clean. On an airless world, shelter isn't mainly about keeping wind out. There is no wind. Shelter changes what a surface can see. It controls how much sunlight can reach the ground and how easily the ground can send energy back into space. That gives the pit an oddly familiar quality. Not because the moon has become gentle, but because the shape of the ground has carved out a quieter arrangement inside the violence. A rocky opening, formed without comfort in mind, happens to hold temperatures that wouldn't feel strange in your own house. And the effect doesn't require insulation wrapped around the pit, or a machine pumping heat from one place to another. Rock, shadow, and line of sight do much of the work. The surroundings remain lunar. The temperature balance inside is local. That little pocket counts because it changes what we mean by an extreme environment. A world can be hostile in the broad view and surprisingly moderate in one carefully sheltered place. Average conditions don't tell you what every surface experiences. Sometimes a few meters of depth or one overhanging wall changes the entire thermal story. If the accidental shape of a lunar pit can hold cold and warmth in such a narrow balance, what kinds of shelter could engineers shape on purpose? You might imagine that a great space telescope mainly needs a larger mirror and better aim. Gather more light, point at the right patch of sky, and wait. But an infrared telescope has a rather awkward problem. It can see heat, and it has heat of its own. Imagine trying to hear someone whisper while you're wearing a jacket that crackles every time you breathe. The whisper may reach you perfectly well. Your own noise simply covers it. A warm infrared telescope does something similar. Its mirrors, instruments, and supporting hardware emit infrared light. That glow enters the measurement alongside the faint signal arriving from space. The telescope can end up blinding itself with light nobody wanted. This is why cold becomes more than a way to keep hardware safe. For an observatory like the James Webb Space Telescope, cold is part of seeing. Webb searches for infrared light from very distant galaxies, forming stars, planets, dust, and molecules. Some of those sources are incredibly faint. If the observatory glowed too brightly at the same wavelengths, the useful signal would be buried beneath light made by the telescope itself. Webb's main telescope must remain below about 50 Kelvin. In everyday temperatures, that means colder than roughly minus 369 degrees Fahrenheit or minus 223 degrees Celsius. Below about 50 Kelvin, the mirrors and much of the observatory become quiet enough in infrared light for the science they're meant to do. One instrument has to go much farther. The mid-infrared instrument, called MIRI, observes longer infrared wavelengths, where warm hardware becomes especially troublesome. It operates at roughly 7 Kelvin, and that is about minus 447 degrees Fahrenheit, minus 266 degrees Celsius. 7 Kelvin is only 7 degrees above absolute zero. At that temperature, MIRI's detectors produce far less unwanted thermal signal. They can notice infrared light that would otherwise disappear into the instrument's own glow. You can view two telescopes aimed at the same dim object. The warm one sees a bright haze made largely by itself. The cold one sees less of its own presence, and the distant source begins to emerge. Nothing about that source has changed. The telescope has simply become quieter. Not every space telescope needs to be this cold. A telescope designed for visible light, X-rays, or other wavelengths has different problems. Even among infrared observatories, the required temperature depends on which wavelengths and signals the instruments are built to measure. Webb's extreme cold follows from the particular kind of faint infrared universe it was designed to see. That makes the engineering slightly absurd in a useful way. You build an enormous observatory to detect some of the weakest heat signals in existence, then discover that the observatory itself is shouting over them. So you cool the mirrors, you cool the detectors, you arrange the spacecraft so the instruments can settle into darkness while the electronics that must stay warm remain elsewhere. But Webb still operates near Earth, where sunlight is plentiful and relentless. Its solar panels need that light. Its communications equipment and spacecraft systems need power. One part must face the sun, while the telescope behind it must remain below 50 Kelvin and MIRI must reach about 7 Kelvin. So how do you keep one side working in sunlight while the other side becomes almost impossibly cold? You might view a thick wall around the telescope, something like the insulation inside a refrigerator, only larger and more serious. But thick insulation alone would still absorb sunlight, warm up, and pass some of that heat toward the mirrors. Webb uses a more careful trick. It gives sunlight only one side of the spacecraft to work on. Between the sun and the telescope sit 5 thin, shimmering sheets. Together, they form a sun shield roughly the size of a tennis court. The first layer takes the direct hit. It becomes hot, but the next layer doesn't touch it across one broad surface. The layers are held apart with open vacuum between them. That gap counts because heat likes a physical shortcut. Put a warm pan on a countertop, and energy moves straight into the counter through contact. That's conduction. Webb denies heat that easy route. With almost no matter between the sheets, very little heat can conduct directly from one layer to the next. Some heat still crosses as radiation, so each layer catches part of it, warms slightly, and sends much of it sideways into space. The next sheet receives less, then the next receives less again. Heat is peeled away in stages instead of being asked to stop at a single barrier. The sheets aren't simply stacked like blankets. Their spacing and carefully shaped surfaces give escaping heat a path away from the observatory. Each gap becomes another small thermal step. By the time energy reaches the shaded side, it has crossed several separate boundaries, losing ground at every one. Across those 5 layers, the temperature falls by about 570 degrees Fahrenheit, around 299 degrees Celsius. The sun-facing layer can be hot enough to boil water. A few feet away, on the telescope side, the final layer sits in deep cold, about 570 degrees Fahrenheit, or 299 Celsius, separates these neighboring parts of the same machine. It's an odd object to imagine. One spacecraft carries 2 different climates, separated by sheets thinner than they look in photographs. On one side, solar panels and warm electronics do their jobs in steady sunlight. On the other, the mirror and most of the scientific instruments remain hidden in permanent shade. The vacuum of space helps, but only because Webb's geometry is so disciplined. Vacuum doesn't automatically make an object cold. Leave a surface facing the sun, and it will absorb energy even when there's no air around it. The shield works because its angle, shape, spacing, and reflective surfaces control where that energy can go. That also means Webb must keep the shield pointed correctly. The telescope can turn toward different targets, but only within a limited region of sky. Swing too far, and sunlight could reach surfaces meant to remain shaded. The observatory's freedom to look around is shaped by the need to preserve its 2 thermal worlds. And the sunshield doesn't do every cooling job by itself. Most of Webb cools passively behind it, simply by staying shaded and radiating heat away. But the mid-infrared instrument needs to be colder still, so it uses a dedicated cryocooler to reach its operating temperature. The 5 layers make that final step possible. They don't create cold as though cold were something stored inside them. They manage heat, giving it a series of exits until very little reaches the telescope. Webb stays cold because its warm side knows exactly where to face, and its cold side is never asked to share the sunlight. It's tempting to treat Webb as a magnificent exception, a machine so unusual and so expensive that its cold side tells us very little about ordinary objects in space. But Webb's lesson is much simpler than its engineering. It faces the same sun with both halves. It travels through the same near vacuum. Yet one face stays warm, while the other becomes cold enough for infrared astronomy. The vacuum hasn't chosen between them. It merely removes most of the surrounding matter that could carry heat by contact or flowing gas. After that, the hardware still has to settle its accounts with light. Think of two parked cars on a clear summer day. Put one in direct sunlight and leave the other beneath a shelter. The air around them may be almost identical, but the surfaces don't receive the same energy. Their temperatures separate because one absorbs more sunlight, while the other has a better chance to lose heat. Space takes away the air, but it doesn't take away that balance. For a spacecraft, the balance depends partly on what each surface sees. A panel aimed toward the sun sees a powerful source of incoming energy. A shaded surface facing dark sky has a clearer path for sending its own energy away as infrared light. Change the angle, the coating, the insulation, or the nearby warm hardware, and you change the final temperature, sometimes by a great deal. That makes Webb's split appearance more than a clever arrangement of parts. On its sunward face, the spacecraft accepts the practical business of being powered, oriented, and kept alive. On its observing side, the telescope has given a carefully protected view away from those sources of heat. One machine carries two thermal environments because its geometry keeps their energy flows from becoming one muddled compromise. So Webb didn't find a convenient pocket of cold and park inside it. Its engineers arranged where heat could arrive, where it would be blocked, and where the remaining heat could leave. The cold observing side is the result of that arrangement. Same sun, same vacuum, a very different thermal answer. That doesn't mean any spacecraft can become equally cold if someone adds enough shiny material and folds it neatly. A mission's orbit, instruments, power needs, pointing demands, mass, cost, and purpose all set limits. Some machines must turn toward warm targets. Some produce too much internal heat. Some have no reason to pay for extreme cooling. Thermal design is always a bargain between what the mission needs and what physics will allow. But the general lesson travels well. A vacuum can help an object hold onto its heat by removing conduction and convection. It can also help an object lose heat cleanly by leaving radiation as the main route out. Which outcome you get depends on exposure and emission, what the object absorbs, what warm things it sees, and what dark directions it can radiate toward. Cold in space, then, isn't a gift waiting in the emptiness, it's an outcome. Sometimes nature arranges it, sometimes engineers do, sometimes the design fails, and the supposedly cold vacuum leaves a sunlit object uncomfortably hot. Once we move beyond one spacecraft and its carefully divided surfaces, though, is there any temperature we can honestly call the coldness of the universe itself? You might imagine that once every nearby star, planet, and warm spacecraft is out of the view, the temperature simply keeps falling. Less light means less energy. Keep moving into darker space, and perhaps there's nothing to stop an object from getting colder forever. But even that darkness contains light. Spread across the entire sky is a faint microwave glow. Your eyes can't see it. Your skin could never feel it. But a microwave telescope can detect it. Point one toward apparently blank space, and a signal arrives from every direction. The sky may look black, yet in microwaves it carries a dim glow from one edge to the other. This is the cosmic microwave background. It's leftover radiation from a much earlier universe, stretched into microwaves as the universe expanded. The name sounds remote and rather imposing. The measurement feels more intimate. An instrument looks into a patch of sky where nothing obvious is shining, and still, there it is, faint, steady, almost the same in every direction. Scientists can separate that background from nearby microwave sources and measure its pattern across different wavelengths. The result matches a nearly perfect blackbody at 2.725 Kelvin, with an uncertainty of about 0.002 Kelvin. That's roughly minus 454.8 degrees Fahrenheit, or minus 270.4 degrees Celsius. Only 2.725 degrees above absolute zero. So part of the phrase "space is cold" points to something real and measurable. Far from stronger local sources, an object doesn't radiate into complete thermal silence. It sends energy outward while absorbing a tiny amount from this microwave field. The exchange goes both ways, even when the incoming side is barely more than a whisper. Darkness, in other words, is not quite the same as receiving nothing. The background remains too faint to notice without careful instruments. Think of a mug cooling in a room. The mug gives off radiation, but the walls, floor, and furniture send radiation back toward it. Lower the room's temperature, and the mug can cool further before the energy leaving matches the energy arriving. The cosmic background plays a similar role, only the room surrounds the whole sky, has no walls, and sits barely above the lowest temperature physics allows. Put a simple object far enough from brighter sources, and it can keep losing energy until its exchange with that background approaches balance. In that limited sense, 2.725 Kelvin acts as a natural radiation floor in the universe today. Empty-looking space still bathes the object in a weak, all-sky microwave glow. There is, however, a useful little awkwardness hiding in that neat number. It belongs to the radiation field. It isn't a temperature automatically stamped onto every grain of dust, planet, or spacecraft floating through space. A grain of dust near a star absorbs starlight. A planet may carry heat from its interior. A spacecraft can face a warm planet on one side and open sky on the other. Even something drifting between stars may absorb other kinds of radiation or produce heat through its own chemistry and electronics. Its temperature depends on the full exchange, every source warming it and every route by which energy can leave. The cosmic microwave background gives the universe a genuine measured baseline. But if that faint glow reaches us from every direction, why doesn't everything nearby settle at 2.725 Kelvin? It helps to think of the cosmic background as the quietest sound in a room. It's genuinely there. Sensitive equipment can measure it. But if a lamp is humming beside you, a heater is running, and someone is making tea, that faint sound won't describe what your ears are dealing with. Temperature works much the same way. An object settles where the energy coming in balances the energy going out. The cosmic background contributes to that balance, but it doesn't get a special vote. It can be overwhelmed by a nearby star, a warm planet, or heat coming from inside the object itself. The strongest nearby influences usually set the terms. Take a spacecraft near Earth. One side may face the sun and absorb intense visible and infrared light. Another side may look toward Earth, which also gives off infrared radiation. Inside, batteries, computers, instruments, and people turn electrical or chemical energy into heat. Meanwhile, shaded surfaces lose energy by radiating it toward darker parts of the sky. So there isn't one useful answer to the question, how cold is space around the spacecraft? The background is present in every direction, but the spacecraft's actual temperature depends on its shape, surface coating, orientation, power use, and surroundings. Even two panels attached to the same machine can settle at very different temperatures. Engineers sometimes have to cool one part while warming another. In a place casually described as freezing, overheating can be the more immediate problem. Planets are even less cooperative. A world can receive very little sunlight and still leak energy left over from its formation. Radioactive elements can add more heat over billions of years. Gravity may squeeze and stir an interior. Tides raised by a nearby moon or planet can bend rock repeatedly, turning motion into warmth. The surface may remain extremely cold, while the deeper layers stay warm. That's familiar in a smaller way if you've ever taken bread from an oven. The crust cools first, because it can release heat directly into the room. The middle stays warm longer, because its energy has farther to travel. A planet is far larger, better insulated, and able to preserve that difference for an astonishingly long time. This is why saying space is 2.7 Kelvin needs a quiet asterisk. It describes the faint background radiation found across the universe. It does not describe every object placed within that radiation. Local conditions usually write the larger numbers. Still, the background isn't merely a technical footnote. Move far enough from bright stars, wait for internal heat to fade, give an object a clear path to radiate energy away. As the stronger influences weaken, that ancient background becomes a larger part of the remaining exchange. It is the floor you approach when the local neighborhood has almost stopped interfering. almost is doing useful work there. Dust, starlight, cosmic rays, magnetic activity, collisions, and stored heat can all keep the surroundings from becoming perfectly quiet. Real places carry histories. A thermometer records the result of those histories, not a universal label attached to emptiness. And that leaves us with a more interesting kind of cold. A distant world may look frozen from the outside, while quietly holding warmth below. So what happens when an entire planet wears a cold surface over a warmer interior? Europa looks like the sort of place where warmth has lost completely. Its surface is bright, cracked, and bitterly cold. The Moon circles Jupiter more than 400 million miles from the Sun, over 650 million kilometers away. Sunlight there is only a small fraction as strong as it is on Earth. From the outside, frozen straight through seems like a fair guess. But the outside is only the lid. Beneath that fractured ice, Europa likely holds a global ocean. It may contain more water than all of Earth's oceans combined. Imagine the Moon cut open. First comes the pale shell, crossed by long reddish-brown scars. Under that sits a dark layer of salty water wrapped around the whole world. Then, much deeper, rock and metal. No spacecraft has drilled through Europa's ice and lowered a camera into that water. The ocean is an inference, though a strong one. When NASA's Galileo spacecraft passed the Moon in the 1990s, its instruments found signs of an induced magnetic field. The simplest explanation is a large layer of electrically conductive fluid below the surface. Salty liquid water fits that evidence well. The ice itself adds another clue. Europa's surface has very few large impact craters, so it appears geologically young. Its long ridges, broken plates, and disrupted patches look like a shell that has shifted and renewed over time. That doesn't reveal every detail below. It does tell us this is not simply an ancient ball of motionless ice. You can think of the frozen shell as a thick winter coat. A coat doesn't make heat. It slows the escape of heat already underneath. Ice can do something similar. Once a layer freezes across the top, it separates the water below from the severe cold at the surface. Heat still leaks outward, but more slowly. The same ice that makes Europa look thermally finished may help protect the liquid beneath it. Europa also has an internal energy source. Jupiter's gravity pulls hard on the Moon, while the gravity of nearby moons keeps Europa's orbit slightly stretched rather than perfectly circular. As Europa moves closer to Jupiter and then farther away, the strength of that pull changes. The Moon flexes. Try bending a paperclip back and forth between your fingers. After a while, the metal warms. Europa is not being bent in quite that way, but the useful idea is the same. Repeated deformation turns motion into heat. Inside the Moon, that flexing can warm ice and rock. Scientists call it tidal heating. We still don't know exactly how thick the ice is, how the ocean moves, or how heat passes between the rocky interior, the water, and the shell. Estimates depend on models, and different measurements leave room for different structures. The presence of water also tells us very little by itself about whether the ocean is friendly to life. Liquid is one requirement, not an answer. Still, Europa corrects the view you get from appearances. A surface can remain deeply frozen while heat beneath it keeps an enormous layer of water from locking solid. The shell and the ocean belong to the same Moon, yet they live under very different thermal conditions. Calling Europa a cold world is accurate, it is also incomplete. The cold describes its face, while the larger store of water may endure quietly below. Enceladus looks even less promising. It's a small white moon of Saturn, far from the Sun, with a surface bright enough to seem almost scrubbed clean. You might view any water beneath that crust as barely liquid, cold, still, and sealed away from anything chemically useful. But material escaping from Enceladus carries evidence of a much warmer place below. In 2005, NASA's Cassini spacecraft saw great plumes rising from fractures near the Moon's south pole. They weren't faint traces of frost kicked off the surface. Enceladus was spraying water vapor and tiny grains of ice into space. Cassini flew through that spray several times, letting the Moon deliver samples from its hidden interior straight to the spacecraft. Among those samples were extremely small particles rich in silica. You've met silica in sand and quartz, but these grains told a more specific story. Experiments and models show that particles like them can form when hot water reacts with rock, dissolves some of it, and then cools. The grains were tiny, but the conditions needed to make them were anything but vague. The chemistry points to water reaching at least about 194 degrees Fahrenheit, about 90 degrees Celsius. That's close to the temperature of water just below a boil in your kitchen. It doesn't mean the whole ocean is that warm. Most of Enceladus can remain profoundly cold, but somewhere near its rocky interior, water appears to enter localized regions warm enough for active hydrothermal chemistry. This is more than water managing not to freeze. It is warm water doing chemical work. Think of a frozen house with one warm pipe running through the basement. The roof can stay buried in snow while heat gathers around that pipe, changing whatever touches it. On Enceladus, the warm zones may sit where ocean water meets fractured rock. There, heat doesn't merely keep water liquid, it helps water and minerals react, exchanging materials as the water moves. The energy comes from inside the Moon. As Enceladus travels around Saturn, gravity repeatedly flexes its interior. The orbit isn't perfectly circular, so Saturn's pull changes slightly along the way. That squeezing and relaxing creates friction and releases heat. Cracks, porous rock, and moving water can then concentrate some of that energy in particular places. Sunlight contributes very little down there. The useful warmth is made locally. Cassini also detected molecular hydrogen in the plume. One likely source is a reaction between warm water and certain rocks on the seafloor. Similar reactions on Earth can provide chemical energy for microbes around hydrothermal systems. That comparison is useful, but it has a firm limit. Cassini found signs of water-rock reactions and available chemistry. It did not find life, and the evidence doesn't tell us how large or stable these warm zones are. What Enceladus gives us is a physical example of warmth surviving where distance from the sun makes the surface brutally cold. The Moon doesn't need to be warm everywhere. It only needs energy to gather in the right places, long enough for water to circulate through rock and come away changed. So the important temperature isn't always the one measured in sunlight, or even the average temperature of a world. Sometimes it belongs to a narrow zone beneath miles of ice, beside dark rock, where water reaches about 194 degrees Fahrenheit, about 90 degrees Celsius, and chemistry stays busy in the cold. Europa and Enceladus can feel like two lucky mistakes. Small worlds, far from the sun, somehow keeping liquid water beneath surfaces that look thoroughly frozen. If sunlight is the only thing in the account, they do look like exceptions, but that account is missing most of the columns. Think of a house on a winter night. The weather outside counts. So does the furnace, the insulation, the warm water moving through pipes, and every open door carrying heat from one room to another. You can't understand the temperature indoors by measuring only the sunlight falling on the roof. You need to know what's happening behind the walls. A world works by the same broad rule. Its temperature depends on every source of energy it receives or produces, how long it can store that energy, and where the energy can travel. Sunlight is one part of that thermal budget. Sometimes it's the largest part, but it isn't automatically in charge everywhere. Inside an icy moon, motion can become heat. Rock and ice bend under changing gravitational pulls. Old radioactive elements can release energy as they decay. Thick layers of ice can slow heat loss, while liquid water can carry heat and dissolved material from one region to another. None of these pathways makes the entire moon warm. They don't need to. They can keep a buried layer active while the surface remains cold enough to freeze almost anything placed upon it. That gives us a useful correction. Europa and Enceladus aren't breaking the rules set by their distance from the sun. They're following a larger set of rules. Once internal energy, storage, insulation, and transport enter the calculation, hidden warmth becomes one possible result of ordinary physics. The surprise came from counting too little, not from nature cheating. Possible doesn't mean common. We can't look at every distant ball of ice and assume there's an ocean underneath. Some may have cooled long ago, some may lack enough internal energy, others may lose heat too quickly, or never have had enough water in the right place. Sunlight still counts, especially near a surface and across long stretches of time. The fuller thermal budget doesn't erase distance. It tells us distance gets a vote, not the whole decision. And this changes what a cold surface can tell you. From outside, a world may appear quiet, fixed and finished. Underneath, heat may be moving, water may be circulating, and chemistry may be working through materials that haven't seen sunlight for billions of years. Both descriptions can be true at once. The surface reading is real. It's simply local. We're used to treating a world's average temperature like a verdict: warm enough or too cold, friendly or hostile. But averages can smooth away the exact places where something interesting is happening. A thin, active layer, a buried sea, or a warm boundary beside rock may matter more than the temperature of everything added together. That leaves us with a wider way to look at any planet or moon. Don't ask only how far it is from its star. Ask where energy comes from, where it collects, what holds it there, and what carries it onward. Once we use that fuller budget, what does habitable mean for life, and for humans trying to survive on worlds that look frozen from the outside? You've probably seen the familiar view. A star sits in the middle, surrounded by a narrow green ring. Too close is too hot, too far is too cold. Somewhere between them lies the habitable zone, where liquid water might remain on a world's surface. That view is useful. Distance really does change how much starlight reaches a planet. Move a world farther out, and the same light spreads across a larger area before arriving. Less energy reaches each square mile of ground, or each square kilometer. But the green ring is a first estimate, not a finished description of warmth. Think of two houses standing on the same street. They receive the same afternoon sun, yet one stays comfortable while the other becomes an oven. The difference may be the windows, the insulation, the roof color, the airflow, or heat rising from a furnace below. Their address tells you something. It doesn't tell you what living inside will feel like. Worlds have their own versions of those differences. A bright surface can reflect much of the incoming light back into space. A darker surface can absorb more. Scientists call that reflectivity albedo. But you already know the effect from walking barefoot across pale concrete and then dark asphalt on a sunny day. The sunlight is similar. The result under your feet is not. An atmosphere can change the balance again. Some gases let visible light reach the surface, then slow the escape of heat at longer wavelengths. A thick atmosphere may keep a world warmer than its distance suggests. A thin one may hold very little, and the details matter. What gases are present? Are there clouds? How high are they? Do they reflect incoming light, trap outgoing heat, or do both at different times? Then there's transport. A planet doesn't merely receive energy and sit politely under it. Winds and oceans move warmth away from bright regions. Rotation changes those flows. Continents interrupt them. Ice can spread, reflect more light, and encourage further cooling. Or warm water can carry enough energy toward the poles to keep parts of a cold world unexpectedly mild. Internal heat adds another route. Radioactive elements decay inside rocky bodies. Tides flex some moons again and again. Heat can rise through rock, feed volcanic systems, or keep water liquid beneath an icy shell where starlight contributes almost nothing. A world outside the usual green ring may still contain places with liquid water and usable chemical energy. They may simply be hidden from the tidy map. None of this makes orbital distance irrelevant. The habitable zone remains a sensible way to narrow a search, especially when astronomers know little more than a planet's orbit, size, and star. You start with the information you have. The trouble comes when that first filter quietly becomes a verdict. Habitability depends on the whole thermal budget: what energy arrives, what the world reflects, what it stores, what escapes, what rises from within, and how all of it moves. Shielding counts too. An atmosphere or magnetic field may help protect a surface, while a buried ocean gains protection from kilometers of ice. So warmth isn't a circle drawn around a star. It's an outcome produced by a working system. Two worlds can share the same orbit and live very different thermal lives. Another can sit well beyond the expected boundary while keeping a dark ocean liquid below. The neat green ring survives. It just becomes what it always should have been, a useful place to begin and a poor place to stop. It's easy to imagine a crewed spacecraft as a very complicated vehicle. Give it enough fuel, thick enough shielding, and reliable engines, and the people inside can make the trip. But a spacecraft is also something more ordinary. It's a small climate that has to work every second. Think about your home on an uncomfortable afternoon. Sunlight pours through one window. A computer warms the room. The refrigerator moves heat from inside its cabinet into the kitchen. You can open a door, adjust the air conditioning, or wait for evening. A crew in deep space can't open a window. Their habitat has to handle heat arriving from outside and heat produced inside. Sunlight may strike one side while the other faces darkness. Engines, batteries, computers, pumps, lights, and scientific instruments all release waste heat, so do the people. Even while resting, every crew member is a small, steady heater who also needs food, oxygen, and water. Insulation slows unwanted heat moving in or out. Shaded surfaces reduce the energy absorbed from the sun. Pumps carry heat through fluid loops, much like water carrying warmth through a household heating system. Then radiators release that heat as infrared radiation. Those broad radiator panels can look almost incidental beside engines and antennas. They aren't. If a radiator can't see enough cold sky, or if exhaust and sunlight warm it, the habitat may struggle to shed heat. The problem isn't that space has suddenly become hot. The problem is that the crew's heat has nowhere useful to go. Location changes the job. Near the sun, a spacecraft may spend much of its effort rejecting incoming energy. Farther away, heaters may be needed to keep fluids, batteries, seals, and instruments within their working ranges. Around a planet or moon, reflected sunlight and infrared heat from the surface join the calculation. A vehicle passing repeatedly between sunlight and shadow must also survive the cycle without letting materials and equipment drift beyond their limits. This is why thermal control can't be peeled away from the rest of mission design. Radiators need area, but area adds structure and affects shielding. Pumps need power, while power systems create more heat. A safer orbit may expose a habitat to a different thermal environment. Even the direction a spacecraft points can change what it absorbs and what its radiators are able to release. Every choice changes several others, which is why engineers can't solve the temperature problem after the spacecraft is otherwise finished. It shapes the spacecraft from the beginning. The same rule follows an astronaut outside. A suit isn't simply warm clothing wrapped around pressure. It's a wearable environment, moving heat away from the body while managing whatever sunlight and shadow are doing around it. Without that machinery, the surrounding vacuum offers no breeze, no cool floor, and no friendly patch of air to carry excess warmth away. So human survival beyond Earth depends on building a local thermal world where none is provided. The walls, insulation, pumps, radiators, power system, and life support all cooperate to hold a narrow, livable climate around warm bodies and warmer electronics. Fuel gets the crew there. Shielding reduces danger. But throughout the mission, from departure to landing or return, survival remains a quiet act of climate control in a place with no climate of its own. Think again of sunlight pouring across black space. The sun hasn't become weaker just because the background looks dark. It is still flooding the solar system with energy. Near Earth, that sunlight can warm a surface, power a spacecraft, or damage anything left exposed for too long. The source is hot. The energy is real. But the space carrying that light is almost empty. It doesn't act like warm air filling a room. It doesn't surround every object with a comfortable temperature. There is no thick atmosphere constantly sharing heat, softening changes, and nudging nearby things toward the same conditions. Sunlight can cross the vacuum. Warmth, in the everyday sense, cannot settle into it like weather. So the answer isn't simply that sunlight is weak. Often it isn't. And the answer isn't simply that space is empty either. Emptiness changes how energy moves, but it doesn't erase the sun or make every object freeze. A hot sun can shine through cold emptiness because emptiness does not behave like hot air. The apparent contradiction disappears once those two facts are allowed to coexist. A powerful source and a cold background don't cancel each other out. Light travels outward through the vacuum. It reaches a surface. What happens next depends on how that surface handles the energy. You can view a dark stone and a polished sheet of metal sitting under the same lamp. The stone may absorb much of the light. The metal may reflect more of it away. If one can release heat easily and the other cannot, their temperatures separate further. Same lamp, same room, different balance. And neither object responds instantly. A thick stone can store energy and warm slowly, then keep releasing heat after the lamp is switched off. A thin piece of metal may change temperature much faster. Temperature depends on what is happening now, but also on what the object has been able to keep from a moment ago. Worlds and spacecraft follow that same ordinary rule, although the bookkeeping can become complicated. They absorb some energy and reflect some. They release energy as infrared radiation. They may store heat in rock, ice, oceans, fuel, or machinery. Some have warm interiors. Some have atmospheres or circulating fluids that carry energy from one place to another. Every one of those details changes the final temperature. Distance from the sun counts, but distance never works alone. Color counts, material counts, rotation counts, an atmosphere counts, internal heat counts, even the shape and orientation of a spacecraft matter. Temperature is the result of the whole energy balance. What arrives, what leaves, what remains stored, what rises from within, and what gets carried elsewhere. This is why one object can overheat in sunlight while another nearby stays bitterly cold. It is why a surface can swing between extremes as it rotates from day into night. And it is why calling space either hot or cold can hide the useful part of the answer. The vacuum is not a giant bath with one temperature waiting to soak into everything. There is no single setting that every nearby object must eventually share. The sun remains powerful. The emptiness still offers no warmth of its own. Between them, each surface and each world keeps its own energy budget. A sunlight keeps pouring across the black. The black stays cold. Imagine the sun once more, pouring light across black vacuum. That light can cross millions of miles of emptiness without turning the emptiness into a warm room. It carries energy. The warming begins when that energy meets something that can absorb it. So how cold is space? By itself, that question has no single useful answer. Empty space does not feel cold the way winter air does. There is too little matter to pull heat from you through contact or moving air. But anything placed there still gains and loses energy. Its temperature depends on the light it absorbs, the heat it gives off, the energy it stores, and the way heat moves through it. That is why sunlight and shadow can sit beside each other and produce such different conditions. A sunlit surface may absorb energy faster than it can release it. Turn the same surface away, and it may radiate its stored heat into darkness with almost nothing nearby to return that energy. The vacuum is not cooling it like a wind. It simply offers very little warmth in exchange. Astronauts live inside that balance. So does the moon. The Webb telescope does too, carefully kept cold while a sunshield takes the light on its warmer side. Even the icy worlds far from the sun follow the same quiet accounting. Energy arrives, energy leaves. Some of it moves inward, some remains trapped for a while. Nothing about that balance requires the surroundings to share one temperature. Once you see that rule, space stops looking like one enormous freezer. It becomes a place where every object has its own thermal life. Two things drifting close together can have very different temperatures because they face different directions, have different surfaces, or hold heat differently. There is no cosmic thermostat making the whole room agree. In fact, there is barely a room at all in the ordinary sense. Just matter, radiation, and a great deal of distance between them. And interiors complicate the view in a useful way. A frozen surface can cover material that is warmer below. Ice may look like the end of the story, while beneath it, Stored heat is still moving slowly through rock, water, or some mixture we have yet to examine directly. The surface tells us what is happening at the boundary. It does not always tell us what the whole world is doing underneath. We know enough to look for that hidden warmth. We do not know every place where it survives, how long it lasts, or what it may allow. Some of the coldest looking places in the solar system may contain pockets where energy has gathered instead of escaped. From far away, they appear still and sealed. Up close, the accounting may be much less tidy. That open edge can remain open. We do not need to fill every dark place with an answer. It is enough to know that cold on the outside does not guarantee cold all the way through. But the main answer is tidy enough. Stars send energy through space. Vacuum carries the radiation, yet it does not become a warming medium like air around a heater. Objects warm and cool according to what reaches them and what they can release. Their surfaces may respond quickly. Their interiors may remember heat for far longer. So when you look at sunlight crossing the dark, you are not seeing warmth spread through a cosmic room. You are seeing energy travel across emptiness, waiting to meet matter. And when it does, the temperature belongs to the thing it meets.